Good afternoon, everyone. My name is Ashwin, and this is Nazi. We work for the big data platform at Netflix, and today we are here to share our experience productionizing Spark for ETL workloads on Yarn. I'm sure most of you here have seen this Netflix page, but did you guys know that Spark contributes to the pipeline that does personal row ordering on this page? We'll go into that application in the second half of the presentation. Not only that, Spark also helps us train some machine learning models which powers our recommendation algorithms. In general, Netflix is a data-driven company. We use data to drive most of our decisions. We collect data from user interaction on devices and also from platforms and microservices that host Netflix. One example where we use data is A/B testing. So let's say we have a UI change. We don't just go ahead and deploy the change and hope that it works out. We rather A/B test it and make sure that it actually improves the experience. The biggest challenge we face at Netflix is scale. Just to give you an idea of at what scale we operate, let me share some numbers with you. So Netflix has over 80 million subscribers in 190 countries. We support over 1,000 devices, streaming more than 100 million hours per day. As you can imagine, this generates a lot of data. But how much data are we talking about? Our data pipeline processes about 700 billion events every day, and this is stored in our data warehouse, which is about 40 petabytes in size. And from our data warehouse, we read about 3 petabytes and write back about 300 terabytes every day. Today, we'll walk you through 3 sections. First, we'll talk about the architecture of our big data platform. Then we'll delve into the technical challenges we faced while productionizing Spark. And finally, we'll talk about ETL. So let's start with the architecture. We basically need to answer 2 questions here. The first question is, how do we get data into a platform? It looks like this. So we have 2 data pipelines. On the top is our event data pipeline. So this is the data that comes from devices and microservices that run out of the cloud. This data flows into our Kafka clusters, and we have a process called Ursula, which demultiplexes this data, merges it, and then stores it in our S3 data warehouse. This data pipeline runs in about 1 minute. And at the bottom, we have our dimension data pipeline. Most of our live data is stored on Cassandra, and every day backups are taken, and we have a tool called Aegisthus, which reads these backups and writes it to our S3 data warehouse. In the end, we have both the event data and the dimension data on S3 ready for processing. So now the second question that we need to answer is, how do we process data? So at this point, we have our data on S3, which is our source of truth. And our predominant file format is Parquet. On top of the storage layer, we have our compute layer. We host large Yarn clusters, and engines like Spark, Hive, and Pig run on top of Yarn. We also host separate Presto clusters, and we have some use cases for Druid as well. On top of the compute layer, we have 2 services that helps us run at this scale. On the left is our federated execution service called Genie, which helps users submit jobs to clusters. And on the right is our federated metadata service called Metacat, and this helps users to get to their data. On top of the service layer, we have a whole bunch of tools. We have tools to move data around, and we have tools for quality, metrics, auditing, and a bunch of tools for visualization as well. At the very top is our interface. We support hundreds of internal Netflix users, and most of them go to the Big Data portal, which is our one-stop shop for accessing big data services. So users can just go to Big Data Portal, pick a compute engine, and then submit a job. It also has other cool features like schema browsing, S3 access, and so on. Under the hood, Big Data Portal uses the Big Data API, and users can directly use that API and get the same functionalities in their applications. We also support Zeppelin and PySpark notebooks. Here is how our Spark on Yarn deployment looks like. So we have over 3,000 nodes on the Amazon that run on the Amazon cloud of type D24 X-large instance type. These instances have about 16 vCores and 120 gigs of RAM. Thanks to Genie, we can run multiple Spark versions on the same cluster. This helps us experiment with new features, bug fixes that are available in the recent versions. And finally, Spark shares the same infrastructure with MapReduce jobs to better make use of our resources. Now let's move on to the technical challenges. The way we're going to do this is we're going to walk you through the life cycle of a Spark application. And as we do that, we are going to talk about the technical challenges we hit. So on Yarn, we have the resource manager process, which is the master process. This manages the cluster resources. And when we submit a Spark application, the resource manager first allocates a Spark application master container and launches it. And then the driver, via the Spark application master, gets an initial set of executors from the resource manager, and then the node manager launches them. In a typical Spark job, you might have used the RDD, or the Resilient Distributed Dataset Interface, which is a core abstraction in Spark. We faced two technical challenges here. One is a limitation of the RDD interface, and the other was a performance optimization. Here's the first one. Recently, we had a use case where we had to merge small files. So we tried to use the coalesce method in the RDD interface. But that method merges partitions by the given number of partitions and not by file size. We used to do that in Hive by using the combined file input format and then setting the max split size. And we wanted something similar in Spark. So we added support for passing in a custom coalescer to this interface, and then we implemented a size-based coalescing strategy, which is what we want. Now let's look at the optimization we implemented in Union RDD. We noticed that simple queries like select star from table limit 10 was taking a long time against partition Hive tables. We looked at it and we found that Spark creates a Hadoop RDD for every Hive partition, and then it groups all those Hadoop RDD into a Union RDD. The problem was that these parent Hadoop RDD partitions were listed sequentially. The problem became worse for some of our tables which had millions of partitions. We fixed this by making the computation of the partitions in Union RDD in parallel. So this fix was good, but we found another important problem in S3 file system, which affected listing performance. So in Hadoop, we found that the file system was making an unnecessary RPC call to S3, which was very expensive. And we fixed this by removing this redundant call. This fix, along with the previous Union RDD fix, gave us a 20x improvement in the input split calculation performance. So this problem was on the read path. We hit another issue on the write path, and this was with output committers. Output committer writes the output of a single task in an all or nothing fashion. So Spark uses the Hadoop output committer where tasks write to a temporary directory, and then the first successful task's attempt's output directory is renamed to the final destination. This doesn't work well with S3 because in S3, a rename is basically a copy and delete. So since we use version buckets, we ended up having 2 copies of the data, and not just that, it was not very performant. And also we had some eventual consistency issues as well. To resolve this, we used our internal S3 output committer, which we plan to open source. And this and here the tasks write to local disk first, and then it's uploaded to S3 when it succeeds. This avoids a redundant copy on S3 and also avoids the eventual consistency issues. So at this point, the driver has finished listing, and it has started running tasks on executors. If you have enabled dynamic allocation, that would kick in and scale your executors up and down based on workload. We've had several major problems with dynamic allocations, and I'm going to talk to you about 2 of them here. Here's the first one. So when dynamic allocation is enabled, we notice that reading broadcast data can take a long time. The reason is executors retrieve block locations from the driver once during the read path, and then they But with dynamic allocation is enabled, replicas can be removed, and then there would be stale entries in the block locations. Here's an example where we have a production job, which took where the reading of a broadcast variable took like 17 minutes. We fixed this on the executor side. So now executors refresh the block locations from the driver after multiple failed attempts. The second problem was related to locality optimization. We noticed that a Spark application failed due to timeouts. So we debugged this, and we found that the application master was canceling and resending container requests when 2 things happen. One thing is if the locality preference is no longer needed, or if the locality preference is not set. Problem is we use S3, and S3 doesn't have any locality information. So this is what was causing the thrashing. We resolved this by basically not canceling container requests which have no locality preference. Now Nazi will come and continue with the technical challenges. Thank you.
Thank you. Hey everyone. So at this point of execution, we have now the tasks running in the cluster within the Spark executors, and now they need to read the data from S3, which is in Parquet format for our infrastructure. And then they do the data flow, they run the data flow, and then they need to write the data back in Parquet format. So here, the Parquet read-write path kicks in, and we have 2 technical challenges here. And the first one is on the read path, which is actually a performance optimization that we have been working on recently, which we call dictionary filtering. So for those who don't know, Parquet is a columnar file format and organizes the data in a hierarchical way. So you have row groups at the top, which is basically a group of rows. And then within row groups, we have column chunks. So for each column in your data set, we have a column chunk. And then within each column chunk, Parquet defines pages, which is the smallest unit of data it manages. And what dictionary optimization does here, and one thing I should mention is like when Parquet writes the data to disk, as you see on the right, it lays out the columns contiguously. So what dictionary optimization does is, so let's say you have some data that can be dictionary encoded first, and then when writing the disk, instead of writing the raw values, what Parquet does is assign integer values to every unique value in a column. And then instead of writing the raw values, it writes the integer values to disk, and then stores the dictionary, stores the mapping at the beginning of the data. And on the read path, when we read the integer values, we just fetch the dictionary and do a lookup to fetch the original values back, which is decoding. So we can describe this optimization with a simple example. So let's say I have a SQL query like select star from my table where state is California, and let's assume that the state column is dictionary encoded. So when we enable this optimization, a SQL engine first can go fetch the dictionary from the disk, which is usually very small in size compared to the data, and then check whether the dictionary contains the value California. And if it doesn't, this means there's no way that the rest of this particular row group will contain a row that matches this predicate. So we can simply skip this row group and then move on to the next one, which will eventually save the engine a lot of CPU and I/O time, noticeably speeding up the query. which we show here. So this is some of the results that we get with some performance tests that we did with this optimization enabled. And we have 3 cases where we first disable the optimizer, the dictionary filtering optimization, and then we enable it with 2 different row group sizes, which is called split size here. So what we notice is when we enable it, we get around 8x speed up thanks to skipping some of the row groups on disk. And then when we increase the split size even further, we get better speeds up to around 2 orders of magnitude improvement. And the reason is we are now able to skip even larger row groups, larger chunks of data during query processing. So overall, if you have a query that has hopefully highly selective predicates against dictionary encoded columns, you'll be able to get pretty good speed ups with this optimization. And enabling this is a little bit involved in Spark right now. So I put this here for reference. So you basically need to enable some filtering parameters in Spark and then disable schema merging. Now that was on the read path. And now I want to talk a little bit about the Parquet write path. So the main challenge that we had here was with dynamic partition inserts. So typically when you do partitioning with Hive, the values of the partitions are statically determined. You hard code them. So and with dynamic partition, what you do is like the values for each partition is determined during execution time instead of determining statically. And this does not play well usually. If you have a high number of these values, this doesn't play well with columnar file formats such as Parquet. And the real reason is, so columnar formats have to buffer entire groups of row group data in memory because on the write path because they need to lay out the columns contiguously when they write. And this may put a lot of pressure on memory because if you have a large number of dynamic values, you need to keep open a large number of Parquet writers, which will allocate row group amounts of memory each, and that will add up to the memory that you allocate within the executor VM, and which may cause application failures due to out-of-memory exceptions. And Spark already has some sort of solution for this, and what it does is it sorts the data based on the partition key so that we have the data clustered based on partition key, and then Spark keeps a single writer open per cluster, and then when it moves to the next cluster, closes the current one, opens a new one, and so forth. But this logic has some limitations. It works well, but it has some limitations that we address here. And the first limitation is if the user has already sorted the data based on the partition key, Spark will blindly resort it again. And we detect this from the logical plan and omit that step. And the second issue that we fixed here is users may want to insert the repartition step before sort, because when you insert a repartition, you may control the number of files in the output, which users typically want because they don't want to have a large number of small files, so they want to merge that. And then we expose this repartition logic at a higher level API, so the users can set it through the data frame writer API. And also we have exposed another config knob to automate this process. Now that the tasks have written their data in Parquet format, so hopefully they finish successfully, and then the job hopefully finished successfully, then we may want to go back and check how the job has performed. We may want to check the statistics, and then may want to tune the job a bit to get better performance. So we go to the history server. And surprisingly, we cannot find our job. I mean, we have seen some production Spark jobs that we have that didn't show up for multiple hours after they completed. So we started digging in. And then what we found is the event log processing is done by a single thread in the history server. So what this means is like if you have an application that has a very large event log, that will keep that thread busy, and other applications will not be showing up in the web UI, in the history server UI. And this is not an edge case. It's very common for Spark apps to have very large log files. In some cases, we have seen like some applications with iterations, like machine learning applications, can easily generate tens of gigabytes of log files. And the solution is to just make this logic, this event log processing logic, multi-threaded, which reduces the latency significantly. And we even further did some experiments to investigate whether GC tunings may help. And then we found that moving to G1 collector and allocating more space to young generation helped reduce the latency even further. Now let's take a look at the ETL part. So at Netflix, we currently run roughly tens of thousands of jobs every day in our infrastructure, and most of these jobs are in Apache Peak, and there are some Hive jobs. And once we productionize Spark, we recently started seeing some production Spark jobs as well. So at the beginning of our investigation, we started with the question like, if we make a switch to Spark, so will we get on par or even better performance? So our first question was performance-oriented. And then for that, we took a number of pig jobs that we have and then have rewritten those jobs in Spark using the data frames API, and then did some performance experiments. So here is one of those pig jobs. And this pipeline loads data from 6 different data sources and then runs some transformations and joins and a series of joins on it before writing the results back. And then we run some performance experiments with Scala data frame API and also the Python data frame API using PySpark. And what we found is like with Scala implementation, we get around 2.5x roughly better performance than Apache Pig running on MapReduce. And the main reason for the speed up is getting rid of the JVM launch overhead, plus better physical operator implementations in Spark thanks to bytecode generation and all the goodies that Project Tungsten brings. And then when we look at the Python implementation with the PySpark APIs, we noticed again a 2x better performance than Pig, but slightly slower than Scala. And when we look deeper, what we noticed is the performance overhead is mostly due to the user-defined functions that we have in our pipeline, which causes the data to be serialized from the JVM to the Python VM and vice versa during the processing, which adds to the latency a bit. So this is just one of the results that we present here for brevity, but we have a number of other results that show similar results, showing that Spark performs better than Pig for most of our ETL jobs that we have picked. Now at this point, we are convinced that we will get at least on par or better performance with Spark. So we then started looking at how we can provide the tooling for our internal users that we support at Netflix, so that when they want to create a new application, they just don't do the heavy lifting themselves, and they use the tools that we provide to them. And this slide shows the production workflow that we roughly follow to create new Spark applications and productionize them. In the first step of this workflow, what our users do is typically start prototyping their applications using the tools that we provide on our gateways or using the notebooks environments that we provide, like the Zeppelin or PySpark notebooks, or even from their IDEs. They just prototype their applications, and then they use the plugins and the tools that we provide them to test their applications. And then after this step, once they have something concrete, they can build these applications using the job templates, the Jenkins job templates that we provide them. And then they can produce these binary artifacts. And then again, using the same Jenkins job templates, they can publish these binary runnable artifacts to S3. And then in the final step, they can go to the Atomic scheduler interface, which is the scheduler which we use mostly in production. They can use the job templates that we provide in the Atomic interface to point to their runnable artifacts on S3, and then they can start scheduling these jobs. And eventually, the Atomic scheduler will download these jobs download these artifacts from S3, and then submit them through our execution service, Genie. And eventually, these jobs will start running on our Yarn infrastructure. Now that we got the tooling for our users starting developing new applications. And I'd like to conclude this section with 2 production Spark applications that various teams at Netflix have built. And the first application is called Yogan, which the application owners define as a rapid innovation platform for targeting algorithms. And what this means is, say, Netflix released a new TV series, and we want to promote this new title to some subset of our users. And the question is, which subset should we pick? And the answer to this question is determined by targeting algorithms and models. And previously, this team was using a mix of pig and hive scripts to experiment with new models and algorithms. But when we productionized Spark in our infrastructure, they migrated these scripts over to Spark, and now they started to get some good numbers with it. And previously, what was taking tens of hours to run some simple similarity calculations against the entire Netflix user base, now it takes only 5 hours with Spark. And similarly, it now only takes just 10 minutes to run some computations against a small subset of our Netflix user base. So obviously, with this specific targeting use case, with Spark now enables us iterate and experiment faster for this use case. And the second application that I'll talk about is ARO, which is adaptive row ordering that Ashwin mentioned at the beginning of the talk. So what ARO pipeline does is to provide a personalized ordering of the rows of titles in the main page. So this is a very large pipeline and consists of a large number of jobs. And what this particular Spark job does is it works towards the beginning of this pipeline and prepares the feature data for downstream consumption. So in particular, it enriches the page and row level data with some of the user's play history features, and then runs some basic transformations on it, and then it pushes it down for downstream processing. So this job is slightly on the bigger side. It has more than 10 stages, and it runs more than tens of thousands of tasks, and it processes several terabytes. So this is slightly big. So at first, when we pushed this job to production, we had a number of performance and stability issues. And then we started working with the application owners to fix both the application and also do some tuning for some of the Spark config parameters. And now this job is running with good performance and reliability every day in our infrastructure. Now I'd like to conclude the talk with some of the future work that we have in mind. And the first item is improved Parquet support. So like we said, we have a lot of Parquet data in our data warehouse. So Parquet read-write path is pretty important for us. And eventually, where we want to get is, we would like to have a performant and reliable read-write path that can operate at our scale. And for that, we would like to continue our optimization work that we have mentioned today. And also, we would like to spend some time on the reliability aspects as well. The second item on our roadmap is better visibility. And currently, Spark also has a nice web UI and a history server UI. But eventually, what we would like to do is to get this execution data into our internal data pipeline so that it lands on S3, and then we can do other engines, other tools that we have to analyze this data and get more insight into what was going on and calculate the metrics that we want. And the other aspect of visibility is data lineage, which we care about deeply. So we'd like to understand which applications are owned by which user and which applications depend on which table. So this is also some useful information to have for us. And the final item in our roadmap is exploring new use cases. So this talk was mostly about ETL processing, but we have a number of other use cases that we have recently started working on and we want to continue exploring. And the first use case is interactive and semi-interactive use cases, where users are submitting queries from their BI tools like Tableau to a remote Spark Thrift server, and where they expect some sort of interactive performance. And the second use case that we care about is streaming. So we would like to understand whether we can provide streaming as a service in our big data platform infrastructure, where hopefully we turn on dynamic allocation and hopefully we share the same infrastructure for Spark and other jobs like Pig and Hive jobs. And the final use case that we want to explore is whether it's feasible to move our current Ursula merge pipeline, which is merging the small files using Apache Hive, whether it's feasible to move this pipeline to Apache Spark. So summing up, so we have walked you through our experience so far with Spark on Yarn for ETL processing, and we have walked you through the technical challenges we had and the solutions we provided, and most of which are open source in Spark 2.0. And in the second part of the talk, we spent time on our investigations within the ETL space. And hopefully this has given you some idea about our experience with Spark so far. And with that, I would like to thank you all again for attending this session, and we'll be happy to take any questions you have. Thanks.
OK, go ahead and raise your hand. I have time for a couple of questions.
Hi, thank you for that talk. It's very enlightening. I had a question. I think it was like the second or third Spark application. You were saying that initially it had a lot of problems. Yeah, that one.
Mm-hmm, yeah.
But then you did some optimizations, and then, now everything's stable. So I don't know. Is that open source A? And then can you maybe talk a little bit more about like what sort of optimizations you did?
Yeah, the answer to your first question is it's not open source. This is an internal pipeline that we run. So this is not open source. The answer to your second question is most of the time when we do optimization, I find myself spending time tuning parallelism. I spend time on tuning the concurrency in shuffle boundaries, or tune the number of partitions with coalesce or repartition. And once in a while, if we hit a bug, then we may need to tweak the memory allocation sizes and etc., those kind of details. But most of the time, you'll spend time playing with your split sizes, number of partitions, and the parallelism that you get in your cluster.
Okay, we'll do one last question.
Hello, my name is Peter Halliday, and our use case is very similar to what you described. I have two questions. You mentioned the Parquet output committer as being something that you're willing to open source. The follow-up question is kind of a timeline on that. And the second is, you described a custom coalesce, and did you have similar plans with that?
So let's start with the second question. The custom coalescer is already open source, but the only limitation is it's only available right now in the RDD interface. So we have some plans to open it up in the data frame and the dataset layer 2. And regarding the second question about when to open source the S3 output committer, is hopefully in our short-term plans. We'll probably work on it in the next quarter or so. So hopefully it won't be long to open it up.
Awesome. Let's give Ashwin and Nezi a big hand.